Alright, so this is an electric energy problem. If Q1 is fixed in place by an insulating stand and has a charge of 7.5 millicoulombs, and Q2 has a mass of 8.2 grams and a charge of 2.4 microcoulombs, what is the distance of closest approach for Q1? So the question is referencing this diagram, Q2, Q1. So Q2 is hurtling towards Q1. They're both positively charged, so you can imagine there's going to be a repulsive force between them. It's moving 220 meters per second. It's going to kind of slow down and then get repelled the other way. And then they're 0.8 meters away from each other. With a problem like this, you got to approach it with energy. It's pretty simple with energy actually, because you just need your conservation of energy statement. We're going to say, hey, E initial is going to equal E final. Well, what's going to be the E final for sure? At the closest approach, it's not going to have any kinetic energy. Initially, it has some kinetic energy. We'll say K initial, and it also has some electrical potential energy between the two, right? For the two charge system here. So it's going to plus U initial, and then at the end, there's no kinetic energy. All of this energy will have transformed into just electrical potential energy U final. So yeah, it's going to kind of slow down and then come to a stop. What we can do is just kind of plug in every equation. 1/2 mv squared plus k q1 q2 over r is an equal k, or r initial is an equal k q1 q2 over r final. So now what I can do, I can just kind of derive an equation for R final, and then just kind of plug everything in. So R final's in the denominator here. What I can do is I can just take the reciprocal of everything, right? No, I can't do that. Never mind. Actually, you can get kind of creative with it. You can get RO here, RO here. So you're going to get a 1/2 mv squared RO. Now that they have a common denominator, I can kind of add them. Q2 over R naught is an equal K Q1 Q2 over R final. Then I can just kind of take the reciprocal here. So I can say R final over K Q1 Q2 is going to equal R initial over all of that 1/2 mv squared plus K Q1 Q2. Yep, that looks right. And then you just multiply everything by K Q1 Q2. So you get, at the end, R final is going to equal K Q1 Q2 R initial over 1/2 mv squared. And I forgot that R initial from when I did the fraction math earlier. I'll make this a little bit easier. You get 1/2 mv squared initial R O plus K Q1 Q2. So that is the equation. You can start plugging everything in there, or you can just fast forward to the next step. And I am curious what this equals. I did this problem. I just want to make sure I did this right. So 9 times 10 to the 12, 9. Okay, yeah, I remember. If you need to know the constant, the Coulomb's constant, check your College Board equation sheet. Q1, 7.5 times 10 to the negative third. Remember that, right? Because we're not dealing in coulombs, we're dealing in millicoulombs, which is always going to be 7.5 times 10 to the negative third. And you can check your College Board equation sheet for that. The reason I do that is just so everything's consistent. I have coulombs, whatever those units are, meters, I will get meters at the end. So it's just keeps everything like nice and easy. Times 2.4, and then multiply that by 0.8, divide that by 0.5 times 0.0082 times 220 squared times 0.8 plus, I'm actually just going to do 162 divided by 0.8, and I got 0.35 meters. I think that's right. Pretty sure that's right. I remember what the answer was here, so I'm just gonna verify. I think this was right. I think this was right. I hope this was right. It seems about. Oh wait, no, it's not right. It's not right. It's not right. It's not right. Just give me 1 second. 129.6 divided by. Okay, wait. Let me just do it like this. Okay. Yes, this is the answer I remember. 0.4 meters, 0.404 meters. That's going to be its closest approach. So it starts at 0.8, and then when it gets to 0.404, like away from the thing, it's going to, actually I'll just do it in a different color. It's going to start moving away. So hopefully, sorry for wasting some time there. I'm going to get straight into the next one. After Q1 rebounds, travels very far away, what will its speed be? So for something like this, what you would do, once again, just another energy statement. Now, after Q1 rebounds and travels very far away, what that's kind of signaling here. So if I do E initial equals E final, what that's kind of signaling is when you're very far away, you have no potential energy because the electric potential energy is KQ1, Q2 over R. When you're like an infinity away or a really large distance away, that potential energy basically becomes zero. So that's just something to keep in mind. You're gonna have all your U. So when you're at rebound, you have all your U final that you just calculated with that number. Well, now you can calculate is going to equal kinetic energy. All the energy is going to be stored kinetically. There's no potential at the end. No potential energy at the end. We're going to do, I guess that means no potential at the end either, but that's a discussion for another day. We're just going to plug in K, Q1, Q2 over 0.404 meters, which we just saw, can equal 1/2 mv squared. Now to solve for speed, I'm going to multiply this side by 2. I'm going to divide both sides by m, and then I'm going to take the square root, and then that gets rid of that. So, this is kind of your final answer. I'm going to plug everything in, and hopefully this all makes sense. So, I get 1/6 divided by that, divided by 2 divided by 0.00. 2 square root. I don't know if that was the right answer. I don't even remember at this point. Is that the right answer? Hopefully it is. I got 312 meters per second, and even if I did some calculator errors there, hopefully this whole process, I don't think that's right, but could be wrong here. Hopefully this whole process of using conservation of energy makes sense. Let me know if you have any questions, as per usual, and yeah, I hope you have a good rest of your rainy day.